Okay, so good morning. My name is Abdulrahim. Today I am a third-year medical student. I will discuss alveolar ventilation. So those are the objectives. So mainly we will discuss ventilation. Ventilation occurs here. So when you ventilate, you bring in oxygen and you remove carbon dioxide. So when you inspire, as you can see, you have zero carbon dioxide. Later, when it gets mixed with the alveolar gas, it increases. However, the partial pressure of oxygen will increase as you ventilate because you are bringing in more oxygen. So moving on, before you inspirate, when you exhale, we will divide the respiratory system to two spaces, the dead space and the alveoli. In the alveoli, we have the alveolar gas, which has composed of 14% of oxygen and 7% of CO2. Okay, so when you exhale, the alveolar gas will leave and it will pass through some of the dead space. So as you can see here, when you have exhaled, the alveolar gas is all over the respiratory system. However, when you start inspiring, the fresh air, which is composed of 21% of O2 and 0% of CO2, will start entering the respiratory system. So in the alveoli, the fresh air will get mixed with the alveolar gas. So as I said, in the fresh air, we have 21% of O2, and in the alveolar gas, we have 14% of O2. So when they get mixed, the percent of oxygen is between 14 and 21. It cannot be more than 21, and it cannot be less than 14. However, in the dead space, which is by definition is the area where there is no exchange of oxygen and carbon dioxide. Therefore, here there is 0% of carbon dioxide. And then after inspiration here, as I said, we have the mixed one, and in the dead space, we only have 0% of carbon dioxide. So by definition, the tidal volume is the volume which you have inhaled. Is composed of the volume which is found in the dead space plus the volume which is in the alveolar gas. The volume in the alveolar gas, we have defined it as the tidal volume minus the dead space volume. Okay, then we multiply them with frequency. Frequency is the rate, ventilation mainly is the same as cardiac output. It's the amount, we have discussed the amount, which is the volume, and frequency is the rate. So we multiply the whole equation with frequency. So as you can see here, we've multiplied both sides with frequency. As a result, we have ventilation. The total ventilation is equals to the ventilation in dead space plus the ventilation in the alveoli. And the alveolar ventilation, we have moved this one to the other side. Okay, so mainly ventilation depends on two things, the frequency and the volume. The frequency and the volume. So if we increase the frequency, what will happen in the ventilation in the dead space? Can anyone answer? So when we increase the frequency, yes, everything will increase. However, if we increase the tidal volume, what will happen? Let's say, for example, we have increased the tidal volume by 100 milliliters. What will happen? How much will the how much will the volume, how much will the ventilation dead space increase, and how much will the ventilation in the alveolar space increase? So the increase will all happen in the alveolar space because the ventilation, the volume in the space is constant. So so we can know here also increases. No, my question is the same alveolar increase exactly. So therefore, we can deduce that the volume can increase the alveolar. So increase in volume has greater effect than increase in frequency. So is it clear? Any questions here? So now we will move to another concept, which is calculation of dead space. Now, as we said before, the okay. So here, after you inspire and before you exhale, you have here the mixed one, which is in the alveoli, and here you have the fresh, which contains 0% of carbon dioxide, because here the diffusion hasn't occurred. However, after expiration, the gas in the alveoli will go up, passing through the dead space, leaving the body. Therefore, in the whole respiratory system, we'll have the alveolar gas. Okay, so here, this F in this equation refers to the fraction, not to the frequency. So here, the FA is the fraction of gases in the alveolar space. FI is the fraction of gases in the dead space. FE is the fractional of gases in the total tidal volume which you have inspired and exhaled. So it's the same thing. The amount of gases in the dead space plus the amount of gas in the alveolar space equal to total volume which you have inhaled. Now those equations are derived from this equation. The doctor said in your recording that he won't ask you, but they are easy derivations. And for me, if I were in your place and if I had a question, I wouldn't use those equations. I will just use this equation and I will solve for the unknown. So if you are interested in the derivations, so here are they. I wrote them in my hand. So this is the main equation, the alveolar volume times the fraction of gases plus the dead space times the fraction equal the total tidal volume times the fraction of gases. Then I've distributed FA. So as you can see here, FA VT minus VD FA plus VD FI equal VT FE. Then I've took VD to one side and VT to the other side. And then I took VD as a common factor, and I took VT as a common factor, and I divided both sides, and I came up with the same equation which the doctor used. So it's the same one for oxygen. However, in the carbon dioxide, there's a small difference. So we said that in the dead space, there is 0% of carbon dioxide. Okay, therefore, Fi of carbon dioxide is 0. Then we did the same thing, and we did the same thing, and we came up with the equation for the carbon dioxide, taking into consideration that Fi is 0. So the doctor said he won't ask you, but if you are interested, these are the derivations. They are very easy. And if you had a question, you can just use this equation and ignore both of those. So are they clear, or do you like me to go in details? Like the takeaway from this slide is just Fi is 0 for carbon dioxide. So this is a checkpoint. So we've said that ventilation is the process by which you bring in oxygen and remove carbon dioxide. The partial pressure of carbon dioxide in the dead space is 0. Of course, if we ignore the exhalation, because in the exhalation, the alveolar gas has to leave. And as you know, the dead space includes the bronchi and the trachea and all the parts where there's no diffusion. So moving on, metabolic rate. So the basal metabolic rate is the demand for oxygen uptake. So mainly from this slide, I want you to know that when you increase the temperature by 1 degree Celsius, there is a 10% increase in the metabolic rate. So 10% of 300 is 30, 30 plus 300 is 330. However, when you decrease the temperature by 1 degree, there's also 10% decrease. So therefore, when they are doing organ transplantation, what do? They decrease the temperature of the organ to the minimum possible to decrease its metabolic rate and elongate its life. So maximum O2 uptake. So as you can see here, you have the work rate, and on the y-axis, you have the ventilation of O2. So as you work more, there is increased demand for oxygen. At one point, when there is no more space that you can diffuse blood, because as we said, the dead space, you will learn in later lectures that dead space can, like the physiological dead space can change. Like some places won't get blood supply. However, when you are working more, there's increase in blood pressure. So those spaces will get blood supply. And this point is when there is no more any part of the alveoli that's getting blood supply. This will be discussed more in later lectures in the circulation. Because if you remember, I told you they will discuss ventilation. Later, there's circulation. In the circulation, you'll understand where the maximum has come. Okay, the respiratory exchange rate is the amount of carbon dioxide that you have produced divided by the amount of oxygen that you have consumed. Okay, so in this equation, I would like to add ATP. So mainly, sorry, this is, okay, so this, let's consider this as ATP. So you use oxygen to produce ATP, and in this process, you are producing carbon dioxide. So if we consider that all oxygen that you have used are being consumed for producing ATP, then this you will use 6O2 and you will produce 6 CO2. And at this time you have a ratio of 1. However, this isn't the case. Normally you have a ratio of 0.7 or 0.8. So what can you deduce from this information? That you are consuming more oxygen than you are producing carbon dioxide. So you can consider, like, let's go back to high school. When we have wasted energy, we'll consider it as heat. So just remember that normally you consume more oxygen than you produce carbon dioxide. For me, I will remember that fast R is 0.7. I won't remember those numbers actually, but however, remember that they are less than 1. So let's say, for example, you have the question about this in the exam and you forget, is carbon dioxide up or oxygen? Or oxygen, is the carbon dioxide in the numerator or oxygen? Just remember, you consume more oxygen than you produce carbon dioxide. Therefore, and the ratio is less than 1. Therefore, the bigger number has to be in the denominator. So is this clear, or do you want me to write it for you? So, okay. So if you want me, I can write it. So as I said, you consume more oxygen than you produce carbon dioxide, and the ratio normally is less than 1. So as you know, when the denominator is bigger, the ratio will be less than 1. So in the exam, if you forget, always remember the bigger number is the oxygen and the ratio is less than 1. Okay, so here is the partial pressure of gases. So you have Dalton's law. Dalton's law. So I'm sorry, am I going fast? Do you want me to slow down? I think like we have covered. So if you want me to slow down, please write in the chat. So partial pressure for gases in gas mixture. So you have total pressure. Okay, is the sum of all partial pressure. So let's consider that here you have oxygen, here you have carbon, here you have nitrogen. So the total pressure is their sum. So it's straightforward. Let me see, we can remove all the links. Okay. So here there's the ideal gas law. So when we are saying ideal gas law, there are 5 assumptions, which are the gases are constantly moving, they have negligible volume, they have negligible intermolecular forces, so forces between molecules, the Dalton, and the London dispersion and those things, undergo perfect elastic collision, that means there's no loss of energy, and have an average kinetic energy proportional to the gas, to the gas's absolute temperature. So the purpose of having ideal gas law is to apply this equation. So Px is the pressure of X times the volume equal M, which is the amount of substance, R is a constant, and T is the temperature. So for sum of dry gases, we subtract the H2O. Then the doctor divided this equation over this equation. When he divided it, we canceled, let's say, we canceled volume V with V, and we canceled RT with RT. And we ended up with Px over Pb minus PH2O over Mx over M. So Mx is the amount of substance X divided by the total amount of substance. So this is the fraction of X. Then he resolved the equation for Px. So simply he just took this one to here. He multiplied both equations with Pb minus PH2O, and he came up with this equation. And from this side, you have just to know this equation. From this equation, you have to remember this, because in the exam, I remember in our exam, which is the 13th batch, we had a question about this. The doctor only gave us Pb, the barometric pressure, and he considered that we already know PH2O, which is the 47, and the fraction of oxygen, which is 0.21. So you can expect a question in the exam about this equation, just having one number. Am I clear? Okay, so here 0.21 times, so here he just like gave you different numbers and he applied the equation. We have similar questions later on. I will have many questions, so if you have pen and pencil with you, that would be grateful. So checkpoint here. So anyone has any questions? So here we have covered. So we spoke about the metabolic rate. We said when you increase temperature, you require more energy. And here, as we said, when you work more, there's increase in ventilation and increase of oxygen intake. Here we spoke that the respiratory exchange ratio is the amount of carbon dioxide that you remove divided by the oxygen that you consume. And we said normally the ratio is less than 1. So if I want to ask you a question, if the ratio is more than 1, what would you deduce from this information? You will deduce that there is increased production of carbon dioxide with increased consumption of O2. You have anaerobic process. And as I told you, remember that the oxygen is being consumed more than carbon dioxide. Therefore, you have, therefore, the ratio is less than 1. Okay, so moving on. So here, when you inspire, you bring in oxygen. Okay, and here considering that there is no pulmonary, okay, I will go back. So I asked a question. I said normally, let's say normally, let's go back. Okay, let's go back. So when the ratio is more than 1, what does that mean? So when the ratio is more than 1, that means there is, let's say, 10 carbon dioxide being produced over 6 oxygen molecules being used. Okay, so when you are producing more carbon dioxide than you are consuming oxygen, what does that mean? That means you are going on anaerobic process. Like, because in anaerobic process, you don't use oxygen. So whose ID ends with 544? Did you get my point? Okay, I'll consider that you got it. So moving on. So here, okay, so here considering there's no gas exchange, so you inhale oxygen, the oxygen enters, the same amount of oxygen that has entered will leave because there isn't any gas exchange, and carbon dioxide, which is in the blood vessel, won't get diffused. However, this isn't the case. What actually happens, you inhale oxygen. The amount of oxygen we have inhaled equal the amount of, the alveolar pressure of oxygen equal the amount of oxygen that you have inhaled minus the amount of oxygen being consumed by the body. So as you remember, we have just discussed it a few moments before, R, which is the respiratory exchange rate, is the amount of oxygen that you use. So is the amount of oxygen that you use. Over it, there is the amount of carbon dioxide that you have produced. So this here, they just changed the form of the equation. They took O to the other side and they divided it with R. So this is like the same thing, just they changed the form of equation. So if you had a question, what's the alveolar pressure of oxygen? And he gave you the amount of oxygen that you have inhaled, and they gave you the partial pressure of carbon dioxide. So, and they gave you partial pressure of carbon. We have a similar question in which for example, you will have these without the partial pressure of oxygen. So my point is, from the alveolar pressure of carbon dioxide, you can find the alveolar pressure of oxygen. We will have similar question. I won't say more consumption of CO2. I will say, mathematically it's correct, but I would say less I will say there isn't consumption of CO2. There's consumption of O2. I was like, you meant more production of CO2. So I won't say there's more production of CO2. However, I will say there is less consumption of O2. As a result, you will have increased ratio. Did you get my point? Whose ID ends with 544? Okay. So here, I'm sorry, I'll repeat what I've said. So here, my point is, from the alveolar pressure of carbon dioxide, you can know the alveolar pressure of oxygen, mainly using this equation. So here they have just, so oxygen uptake is the same as partial pressure of carbon dioxide divided by R. We will have similar questions, don't worry. So here, considering that R is equal to 147, which is, this is also assumed, minus 40, which is the assumed the alveolar pressure of carbon dioxide equal to 170. Subtracted them. However, when it is not 1, you have to divide by R, because any number divided by 1 is the same. If it is not 1, you divided it and you find it. So here, as you can see, when R is 1, so the same amount of oxygen that you have, you are exhaling an equal amount of carbon dioxide. However, here you are using more oxygen and you are using more oxygen for the same amount of carbon dioxide. Therefore, this number has decreased. So you can also apply those tricks to make sure that your answer is correct. Did you get my point, or do you want me to repeat myself? So when we said when there is R is the exchange rate. So when you are using more oxygen to, please repeat. Okay, so let's say R equal 1. So you are using 10, so you are producing 10 carbon dioxide and using 10 oxygen. Okay, therefore, the oxygen consumption, you are consuming 10 oxygen. Okay, so here we said that the alveolar pressure is the amount of oxygen that you have inhaled minus the amount you have consumed. So here you are consuming 10. However, now let's consider that R is not 1. Okay, or let's consider that it is not 1. So here you have 8. And here you have 10. Let's 1 minute. Let's to make things simple. So here you have 10, and here you have 12. So to produce the same amount 10, you are consuming more oxygen. So when you are consuming more oxygen, you are subtracting by a greater number. Therefore, this number is less than this number. Did you get my point? And I know like sometimes numbers aren't that easy, but using like sometimes you can use those, not because R is less, because you are consuming more oxygen. So here, you said the partial pressure, the alveolar pressure of O2 is the amount of O2 that you have inhaled minus the amount of O2. This one is the amount of O2. This one, O2 uptake minus the amount of O2. So when R is less than 1, we said when R is less than 1, that means the O2 uptake is more than CO2. Okay? Therefore, you're using more oxygen. When you're using more oxygen, you are subtracting by a greater number. Therefore, this number is less than this number, whose ID ends with 586. Did you get my point? Now, for the alveolar pressure of PCO2, there's a different equation which you aren't required. How they came up with it, but you are only required to know this one. So here, VCO2, which is the amount of carbon dioxide which leave from the circulation to the alveoli, divided by ventilation. So as we said at the beginning, when you ventilate, you are removing carbon dioxide, correct? And your body is producing carbon dioxide. Okay, so when you ventilate more, what will happen with the partial alveolar pressure of carbon dioxide? Will it increase or decrease? So when you ventilate more, what will happen with the alveolar pressure of carbon dioxide? It will decrease. Okay, and when your body is producing more carbon dioxide, what will happen with the alveolar pressure of carbon dioxide? Will it decrease or increase? It will increase. So therefore, let's consider for, of course, multiplied by 863, and you have to memorize this number. Let's say, for example, in the exam, for any reason you forget this equation, just go back to the basics. You ventilate more. The alveolar pressure of carbon dioxide will decrease. Therefore, this one has to be inversely proportional. So one has to be up, the other has to be down. When your body is producing more carbon dioxide, the alveolar pressure of carbon dioxide has to increase. Therefore, both has to be in the numerator. So if you forget, if you don't memorize, just go back to the definition, and hopefully you will come up with the equation. So here we have an example, patient with a normal metabolic rate and depressed brainstem. So with depressed brainstem, they mean that the ventilation isn't occurring as usual. It's occurring at a less rate because the ventilation is controlled by the brainstem. So the amount of CO2 produced is normal. However, the ventilation is reduced. So here, what's the alveolar PCO2? So mainly just want you to apply the previous equation, which is 225, which is the amount of CO2 produced divided by ventilation times 863. So alveolar ventilation, the same equation. And here, however, here, they have considered that VA is unknown, and they've solved the equation for VA. So did you understand what happened here? So here, so in the previous equation, the PCO2 was unknown. However, we solved it and found it 86.3. However, now they want to find VA. What did they do? They just redistributed. They multiplied both sides with VA and divided them with PaCO2. And then they divided 225 over 86.3 times 863. So here, this is a graphic illustration of what we have discussed. So as I told you at the beginning, when you ventilate, you are bringing in oxygen. Therefore, as you see, when you ventilate more, the alveolar pressure of oxygen increases. However, when you ventilate more, the alveolar pressure of carbon dioxide decreases. Is it clear? So, okay, definition of alveolar ventilation. There's a question about this slide. Normal ventilation. So, how is ventilation calculated? Ventilation depends on the alveolar pressure of carbon dioxide. So, when the alveolar pressure of carbon dioxide is normal, considered as normal ventilation. When it is reduced, hyperventilation. When it is above normal, we consider hypoventilation. So we are only looking on the alveolar pressure of carbon dioxide. However, hyperapnea is defined as increase in ventilation. You are ventilating more without changes in PCO2. So as I told you, ventilation depends on CO2. However, if you are exercising more and CO2 is unchanged, we don't say hyperventilation, we say hyperapnea. Tachypnea is only respiratory frequency. So usually when you exercise, you don't hyperventilate, you hyperapnea, because there's increased production of CO2. Therefore, you need an increased removal of CO2. Therefore, you have an increased ventilation to maintain a constant pressure of carbon dioxide. Am I clear? Okay, here we have a question. Can you repeat? So, so ventilation depends on the pressure of alveolar pressure of carbon dioxide. Okay, So here, normal ventilation, carbon dioxide is normal. Hyperventilation, carbon dioxide is below normal. Because as we said in the previous slide, when you ventilate more, the pressure of carbon dioxide decreases. Therefore, hyperventilation, there is reduced carbon dioxide. Hypoventilation, you are ventilating less, there is increased carbon dioxide. Okay, so for some reason, you are ventilating more. However, the pressure of carbon dioxide is normal. You don't say hyperapnea. You don't say hyperventilation, you say hyperapnea. So when you exercise, so now we are exercising. Let's go back to this slide. I am exercising. As a result of the increased work rate, I ventilate more. And this, when I ventilate more, because my body is producing more carbon dioxide and I have to get rid of this increased amount of carbon dioxide to maintain a constant amount of carbon dioxide in my body. So in this case, I am ventilating more. However, the pressure of carbon dioxide is normal. I say hyperapnea because there's increased ventilation and there's no change in PCO2. Did you get my point? So takeaways: hyperventilation, reduced pressure of carbon dioxide; hypoventilation, increased; hyperapnea, increased ventilation without change in PCO2; tachypnea, it's just a respiratory frequency, which was part of our equation, first equation. We said the volume times frequency, tidal volume times frequency equal dead space volume times frequency plus alveolar volume times frequency. So in exercise, there's no hyperventilation, there's only hyperapnea. So this is an equation, this is a question. So here, what do we have? Someone is in the mountain. The barometric pressure is 647. And the inspired PO2, what's the inspired PO2? So this is the equation. So does anyone know the answer? I told you about this equation. They will give you only one number and they expect you to have memorized the other two numbers. So if anyone C, which is 126. Yes, excellent. So 647, which is the barometric pressure, minus the pressure of H2O, which is 47. You should have memorized this number, times the fraction of oxygen, which is 0.21, which also you should have memorized this number, equal 126. So this is another equation. Here you have, no, you have to use the calculator, which is found in ExamSoft. For me, in the exam, I would bring paper and pencil and I would solve them by my hand and just enter the last step. Because if you want to depend solely on the calculator, if you did a mistake, it would be hard to find it. So here, this is another question. What is the alveolar pressure of O2? Consider that respiratory rate is 0.8 and the PCO2 is 32. Those are from the slides. So does anyone know the answer or have solved the answer? So you have to use this number, 126, which you have already found. So any answers? I think we can move out A. Excellent. So 126 minus 32, which is this one. No, sorry, this one here. So as I told you, this one here. So to find the alveolar pressure of oxygen, you can find it from the pressure of carbon dioxide being produced, divided by R. Okay. So here the key concepts from this lecture. The alveolar ventilation is the volume of fresh non-dead space gas entering the respiratory zone per minute. It can be determined from alveolar ventilation equation. That is the CO2 output divided by fractional concentration of CO2 in the expired gas. So you can read these key concepts. If anyone has any question, can ask me. Can you repeat the last question? So mainly here, we have, sorry, this is the last question, okay? In the question before, we have calculated the PiO2, which is the amount of oxygen that you are inspiring, which is 126. So here, what did we do? We used, we used this equation. This equation, the amount you have inspired, 126 minus the pressure of CO2, which was given, and the R. So here, the pressure of CO2 is 32 and the R. They divided 32 over R, then they subtracted it from 126. Did you get it? Or do you want me to write it? So that's okay. So here, so does anyone has any questions? So here, we said the anatomic dead space is the volume of the conducting airways. Therefore, when you are exhaling, the dead space includes the alveolar gas, because the alveolar gas has to pass through the conducting airways to leave. It's measured. Okay, so here we have questions. So questions, do you want 5 minutes breaks? If you want 5 minutes breaks, you can have one. For the questions, most of them are calculations. So I prefer that you have paper and pencil with you. Okay, so this is the so no one has answered. So this is the first question. A normal subject has a pressure of CO2 of 40 millimeter mercury. Voluntary doubles his respiratory frequency, but does not change his tidal volume, assuming no change in metabolic rate when he comes to a new steady state. What his arterial pressure of CO2 is most likely to be. So here there is double his respiratory frequency, but does not change his tidal volume. So what do you expect to happen in the CO2? So any answers? Anyone would like to try? Shahid is the host here? I don't get the questions. Oh, sir, they're still here. So mainly, I thought that, okay, so a normal subject doubles his respiratory frequency. So if we said, you are close. When you double the frequency, when you increase ventilation, what will happen in the carbon dioxide? The carbon dioxide should decrease, not increase. So normally you had 40. So when you have doubled the frequency, it should decrease. Yes, that's 20. So as I told you, when you have questions, go back to the basics. Ventilation, removal of carbon dioxide, inhalation of oxygen, increase in ventilation, increase in oxygen, decrease in carbon dioxide. So yes, it's 20. Because if we go back to the equation, the ventilation is composed of volume and frequency. So when the frequency increases, the ventilation will increase in the same rate. This is ventilation, and this is volume. That's my handwriting isn't that good. So this is the equation. So as we said here, ventilation is composed of both volume and frequency. The ventilation will increase in the same rate as the frequency. And in ventilation, there is decrease in carbon dioxide and increase in oxygen. So in this question, if the question was about O2, yes, the answer would be 80. So with no change in respiratory minute volume, the alveolar ventilation rate may be increased by an increase of. So this is the same equation. Here we are saying there is no change in the frequency. What other thing can increase? Yes, tidal volume. Excellent. Those questions, by the way, can come in your exam. Most of them are from the PDF which Dr. Hashim have gave you. So they are Dr. Hashim style. Okay, so there's a depression in the CNS. In response to anesthesia, there is usually depression in CNS. With respect to respiration, what would you expect? What would you expect to change? Excellent. Yes, it's E. Because as we said, depression in CNS, we said that ventilation is controlled by the CNS. So there is depression, therefore there is decreased ventilation. And we said, and I've emphasized it enough, that ventilation is calculated depending on carbon dioxide. So here is it. Ventilation is calculated ventilation depends on the carbon dioxide. Excellent, who said E? A 38-year-old non-smoking woman complained of dyspnea and shortness of breath when climbing stairs. As part of a thorough pulmonary function evaluation, her physiological dead space was measured using a spirometry. The physiological dead space is defined as, okay, this one is easy. No. When you say no, the D isn't correct. B. Okay, so we have B and C. It's B. It's the place where there's no ventilation occurring. So as we said, ventilation depends on carbon dioxide, and the volume of lung which does not eliminate carbon dioxide is the place which ventilation does not occur in, which is B. The volume of lung which is perfused but not ventilated is wrong, because later you will learn that the upper part of the lung is ventilated but not perfused. The lower part of the lung is perfused and ventilated. However, ventilation occurs in the, let's forget ventilation. Let's say gases are found in the whole part of the lung. And perfusion is where, let me repeat here one point. So the volume lung which is perfused but not ventilated, not the whole lung is perfused. There's areas which are not perfused. Let's say, for example, we said that the trachea is a dead space. Is the trachea perfused? Can anyone answer me in the chat? Is the trachea perfused? No, therefore, this is not the definition of a dead space. However, the definition of dead space is the area where ventilation does not occur in. By definition, ventilation is determined by the pressure of carbon dioxide. So here, as we said, here the fresh air is the dead space where there is no carbon dioxide. Okay, so here, a 76-year-old woman with a 4-day history of pneumonia was referred to pulmonary arterial blood gas is 52 for oxygen. The O2 saturation is 87%, pH 7.53. arterial pressure of carbon dioxide is 30, bicarbonate is 24, which is the most reliable indicator for her alveolar ventilation rate. So it's the same concept. So here we have different parameters. Which one of them is reliable for alveolar ventilation rate? D. So it's the same concept. So we have 3 questions about the same concept. Hopefully in the exam, it will be easy. So this one is from Dr. Hashim. This one isn't mentioned in the lectures. However, this number is the answer here. It's 22.4. Yes, this number, I have memorized it in my high school. But why did he put it? I don't know. I am not sure, but I think we had this question in our exam. Can you repeat the last question? So here we have different parameters of oxygen, pressure of oxygen, saturation of oxygen, pH, alveolar pressure of carbon dioxide, and bicarbonate. Which one is reliable indicator of alveolar ventilation? So there's a previous group of questions. We're focusing on one thing. Which is the ventilation rate is dependent on carbon dioxide. So did you get the question? The one whose ID ends with 620. So it's all the same thing. We are saying just it's dependent of carbon dioxide, but this time you had the question as numbers. And this one, 22.4, you should just memorize it. Okay, the world highest summit is 29,000 feet, and the barometric pressure is 247 millimeter mercury. 2,000 climbers have reached the summit, and 200 have died trying. On May 8, 1978, Reinhold Meister and Peter Haber achieved what was thought to be impossible, the first ascent of Mount Everest without oxygen. The inspired. Okay, so E. Any other answers? Anyone like to try? So it's the same concept. They will give you one number, and they expect you to know the fraction of oxygen and the pressure of H2O. So yes, the answer is C. So here, the same concept. The pressure of oxygen equal the pressure of oxygen equal the fraction of oxygen in air multiplied by the barometric pressure minus the pressure of H2O. So it's the same concept. Oh, this is okay. This is a mistake. If Mason and Haber had not hyperventilated, their RT PCO2 would have been at sea level at 40 millimeter mercury, assuming that R is 1. What would have been their alveolar PO2? So here in the previous question, you found it as 42. So here what they did is 42 minus 40. So PiO2, we found it as 42 here. And here they considered R as 1, and they considered the pressure of carbon dioxide as 40. So 42 minus 40 is 2. So is this question clear, or do you want me to repeat it? Or do you want me to solve it with my hand? Okay, so the same thing. What fraction of oxygen do climbers have at Mount Everest, 147? Need to have a normal value of 150. So here we are solving for the fraction of FiO2, which we have considered previous to be constant as 21%, but now it has changed. So does anyone have any answer? Can you? Okay, I'll ask if. Okay, 1 minute. Give me a minute, please. Okay. I'm sorry for this. 1 minute, please. Okay, so I've changed that answers will be only for the host and the co-host. So send them to me, to the co-host, not to the host, because the host is another person. Okay, so the answers are A. A is, yes, excellent. A is correct. So here they just solve for FiO2. Think it's simple math. So here a 15-year-old student complaining of dyspnea was admitted to the ER because he appears cyanotic. His arterial blood gas were determined. The results are PaCO2 is 52, the pressure of oxygen is 70, pH 7.3. The metabolic rate was 250 millimeter per minute, and the R is 0.8. What is the calculated alveolar ventilation of this patient? So, okay. So, any answers? So the alveolar ventilation, as we said, is pressure of policy. So here is it. So here are the given, and here this question requires two equations. So here are both equations which require them. So the alveolar ventilation is the ventilation of carbon dioxide divided by the pressure of CO2 times 863, and R is the amount of CO2 produced over O2 consumed. So here you have to use both equations. So from the first equation, you have to find CO2, and then you have to apply the second equation. C, excellent. C is correct. So here is it in detail. So you have to use both equations. The alveolar ventilation, which is the amount of CO2 produced, amount of the, which is the alveolar ventilation, which is the, sorry, the split is the amount of CO2 produced over O2 consumed. The ventilation is, which is the amount of CO2 that's diffused over the CO2 which is removed, times 863. So here first we found the amount of CO2 produced. Then in the second equation, we divided 200 over 52, which is the arterial pressure of carbon dioxide times 863. So is it clear? So thank you. That's it. Any questions? I'm sorry, what's your question? I'm sorry, I didn't see it. I have a question. PaCO2 is the amount of O2 uptake. PaCO2 is the amount of O2 uptake, PaO2, right? PaCO2 is the amount of oxygen uptake. So PaCO2 is the amount of oxygen. So 1 minute. What you are saying is their question is correct. I mean, they are equal in one case. Yeah, they are equal in one case. You have to answer me. They are equal when R is 1. When R is not 1, you have to divide the CO2 with the amount of R. So 1 minute. So here. So this is the part you are asking me about. So they are equal if R is 1. However, if R is not 1, you have to divide the PaCO2 with R to find the alveolar pressure of oxygen, to find the pressure of oxygen being used. Does that answer your question?
Yeah, that's exactly what I'm asking about. Thank you.
Yeah, okay.
Yeah. So we use this to figure out what PaO2 would be.
Yes, so it's mainly what the equation says. The equation says the alveolar pressure of oxygen is equal to the amount of oxygen which you have inhaled minus the amount of oxygen being used by your body. Okay, the amount of oxygen being used by your body is this one, which is equal to the amount of oxygen, carbon dioxide produced divided by R. R is the respiratory exchange ratio.
Okay, perfect. Crystal clear. Thank you.
Okay, so as we said here, the alveolar pressure of carbon dioxide is dependent on the amount is the inverse proportion to the ventilation and direct proportion to the amount of carbon dioxide being produced by the body. Direct proportion to the amount of carbon dioxide being produced by the body. So here we have changed the equation to find VA. For me, I would only memorize one equation. I would memorize this. If I were in your place, I would memorize this because I can understand it, and then I would solve for whatever is unknown. And I wouldn't memorize the same different forms for the same equation. I will only memorize the one which is physiologically relevant. In case I forget it, I would go back to the concepts and figure it out. So, okay, so that's it. So can you go to slide 23? Slide 23. Okay, this one. You can open your mic, you can unmute yourself and ask.
Yeah, I just wanted to check something. It's clear now.
The last part will be discussed later. Okay, so those questions, as I told you, they are from Dr. Hashim, and you can have similar ones. But usually he doesn't bring hard questions in the exam. He will bring those, if you want to bring such questions, he will bring them in the TBS. Okay, so if anyone doesn't have any question, I think we are done. So, is the host with us?
Actually, I have a question. I just asked about slide 23, where it talks about hypoventilation, hyperventilation, and so on. In these situations, we determine what kind of ventilation it is based on the arterial pressure, not the alveolar pressure, right?
May you repeat, please?
Yeah.
The same slide. This one.
Yeah. Is my voice clear?
Yeah, it's clear.
Okay. No, not this one. It's slide 23, the one with the hypoventilation and hyperventilation. To determine what kind of ventilation it is, we look at the arterial pressure, right? Not the alveolar, yeah.
PA usually Dr. Hashim with small a, he refers to arterial.
Yeah, that's what I meant.
I don't think he would ask you like both of them together. So just like ventilation, when you are ventilating, you are removing more carbon dioxide. You are removing more carbon dioxide from the body. So therefore, in the body, it would decrease. So usually, like, don't focus. For me, I wouldn't focus on those small details. Like, just like understand it. So more ventilation, increased removal of CO2. Therefore, the CO2 would decrease in the body.
Okay. All right. Thank you.
So I don't think like he will ask you, is this alveolar or arterial? Don't think he would go to those details. Usually, in the alveolar pressure of CO2, after exhalation, usually it doesn't reach zero. It doesn't reach. Okay, so any other questions? So I think if the host with us.
Yes, hi. Should I stop?
I think if no one has any question, yes, we can end the session.